Hello, today we're going to be talking about flight software. This is the EPET 401 module 10. And last week we discussed about flight hardware. And this week we're going to join the flight software with that hardware to make a functional spacecraft, functional mission. Here's just a bit of an overview of what we will cover. So we will be talking about what is flight software in general. Then we will be covering flight software in particular for the PyCubed, then for the Beaglebone, and then we'll discuss about the other software frameworks that are out there. We'll discuss about software best practices to make sure we develop good software. And then we'll discuss a little bit about our mission again. On the right, you can see just two snapshots of the development environments that we use for the PyCube and for the Beaglebone Black, just as an example of how you program for these boards. All right, let's jump into it. Let's talk about what is flight software and how can we go about it. So flight software is the software that runs on the spacecraft's onboard computer. Like we discussed last week, the onboard computer is the brains of the software of the satellite, and the flight software makes the brain function. So this is responsible. Flight software is responsible for managing everything on board. So this means the data processing, the commands, the health, spacecraft health, even failure and recovery of the spacecraft is what needs to happen. So flight software is critical. Flight software makes the spacecraft become live. So on the right side, we have just a couple of screenshots of mission operation software that communicate with the flight software on the spacecraft. The flight software in the spacecraft generates all the data that we will be processing on the ground to then make decisions and send new commands to upload new commands to the spacecraft. So other functions that are important to highlight. So the flight software on the spacecraft processes incoming ground commands, like I just mentioned. It processes storage and transmission of engineering data, or sometimes called telemetry, but also the science data. So everything that is data is handled by the software. And then this software sometimes is not just run on the primary onboard computer, but it's also run on the various subsystems. So like the attitude control system, the power system, it also can have its own software. And one important aspect of software is also the fault detection, isolation, and recovery. Sometimes it's shortened by FDIR. So it's important to develop software that could potentially recover, say, a possible reboot, unexpected reboot with a single event upset, or even things more serious like a sensor on your spacecraft stopped working and you're relying on it. If you don't have that sensor, are you going to completely damage your spacecraft, or are you going to be able to continue to operate, even if not perfectly? Can you continue your mission? So these are things to consider when you're developing flight software. So today, with more capable onboard computers, flight software has also become more capable and more demanding. And it's important to realize this. It's before, with very small flight computers or very not so capable flight computers, software might not actually be that sophisticated or complex, but today it is becoming a major endeavor. one of the aspects that is highly discussed in flight software development is the ability to run in near real time or real time. And this means that when you have, say, your computer, our computers like MacBook Pros and a Windows machine, Windows and Linux and Macs are not necessarily real-time operating systems. They feel like it, but they're not. Because if you're running Zoom or if you're running Chrome or some other app in your computer, it's actually blocking other applications from running. So that could create a delay in a new application. Say you open your mail client, and it takes a few amount of seconds to load. Now, opening a mail client is not necessarily a critical task, but for a spacecraft, if that spacecraft needs to fire a thruster or send a command to the ground station or some telemetry to the ground station, and you have a short window of opportunity, a delay in the flight computer can actually be a critical impediment to your spacecraft operations. So we want the flight computer and the flight software to run as real time as possible. And then there's hard real time, and then there's soft real time. We will not dive too deep into these, but just so you know that this is something to consider. In most of the spacecraft applications that we are dealing with here at the Hawaii Space Flight Lab, we are just dealing with soft real time, which is good enough for the missions that we currently have. So what this means is that the onboard computer must supervise different inputs on the spacecraft and outputs, and you have to guarantee that exchange of data does not exceed a specific amount of time. So it could be a fraction of a second, maybe a second. A second would be actually quite a lot. So flight software must be reliable and predictable throughout the lifetime of the mission. We don't want flight software to start to become laggy and slow after a day or 2 days. This could mean that there's a bug or a memory leak or something like that. We want the flight software to remain constant as much as possible. And we want it to be deterministic and reliable. So these are all qualities of flight software that we care about. So let's just discuss a little bit about how do you select the right flight software, or how do you develop your flight software. One aspect is the amount of memory and the computational resources that you have. So if you have a very tiny amount of memory, you cannot install Linux on that computer if you only have like 32 kilobytes. You have to have a few hundred megabytes of memory to be able to run Linux or some other operating system. So there's some onboard computers that don't run operating systems and cannot operate like large flight software frameworks. And that's okay. So it just depends on what's available. You also want to consider financial and schedule factors. So many times software is hard to predict how costly it can become and how long it takes to develop. So it is important to at least do a best effort to plan flight software development to guarantee that it fits within the budget and scope of the mission. Many times we rely on past experience with a particular software framework because we understand it, and there's no need to train engineers in a new software framework. So the learning curve is usually a time sink. So there has to be very strong reasons to choose a particular flight software over another one. Another factor is the maturity of the software. If it has been tested and used in space before, that's something very, very useful. And then availability on the target onboard computer. So if your software will not run on your target onboard computer, there's no purpose. So there's a bit of research there that has to be done, or experimentation. So we have these two processor types, the microcontrollers and the microprocessors on the left, and then the most advanced computers like ARM and x86 processors, like the Beaglebone Black. So on the left, going back to the microcontrollers, these are typically, the flight software is typically developed in C or assembly language. So it's very low level language, closer to the hardware, very efficient, and very capable in many other ways. Now we're also experimenting with MicroPython or CircuitPython for the PyCubed, which is, I would call it an experimental effort. There's no operating system on these. Usually you run it on a single thread, bare bones in the hardware. And then the development environment for these are very specific. So usually the vendor will give you an actual development environment to work on. So MPLab is one example for the microchip family of PICs. The TIC Studio is another example. So it's just important to realize that it's not, these might be low level, but they require actually some highly specialized tools to program. So you have to realize that because microcontrollers have very low memory footprints, it is important to keep your code base small and very efficient. So sometimes this actually requires more knowledge of the hardware and more intricate development. So this is highly specialized and optimized software. The development and testing is also challenging because sometimes you cannot fully test your software in that particular development environment, and it takes quite a bit of time to actually push that software. So it's something that MicroPython is actually, could be actually very useful in shortening that development time. These code bases usually are between 10 to 20,000 lines of code. Okay, and jumping to the right, we have the more capable processors. More capable also means that they will consume more power. So sometimes they're not feasible for CubeSat mission. It depends on the power budget and availability. But these certainly have become more popular with small satellites and in particular CubeSats. So this flight software typically is developed in a higher level language, so C or maybe even C++. And many people are experimenting with Python. That's could also help to shorten the development time. Python is usually not as efficient as C++, but for certain applications, it holds promise. So now you can actually install an operating system such as Linux. And if you really need that more real-time capability, you can install some other operating system, like a real-time operating system, such as Vxworks, RTEMS, or FreeRTOS. These are quite common in the airspace industry. RTOS has been designed to operate in minimal processor and memory environments. So actually RTOS or FreeRTOS and RTEMS, some of them will work in microprocessors, not necessarily microcontrollers. So there's some back and forth here with these real-time operating systems. Now, the code base for these higher level processors usually goes to 50, 70, 100,000 lines of code. It's much more code to manage and handle. So the complexity is significantly higher. So let's talk a little bit about these operating systems and what's available out there. So we have Linux. Linux is an operating system that has been used in several spacecraft. So you can see here on the right, I took a table from a paper from Hannu Lepinen. And these spacecraft have all been, have all been flown in space. It's not experimental or anything like that. It's actually going up and executing successful missions. You have several CubeSats here, like the Strand 1, LightSail, and then you have the Dove satellites. These are commercial satellites that take pictures of the Earth. Then you have the Falcon Dragon and SpaceX. So, Linux is certainly very capable and can be customized to the scale of the mission as well. So Linux has been deployed in x86, PowerPC, Leon, and ARM-based processors. So many architectures are there. It's been widely used in government and commercial applications. There's a particular distribution of Linux that it's like Linux from scratch, where you can customize exactly what you want to put in the Linux kernel. This is called Yocto, and it's been used in the Xilinx Inc. We have actually used that on Neutron 1 and now on HiTi. So it's widely used, and Debian is another distribution that is quite common. So like the Beaglebone Black and the PowerPC can run Debian. For those that really need the real-time extension, there's this module, Xenomai, that improves the critical time performance, because again, Linux is not necessarily a real-time operating system. It's a soft, or not even soft real-time. So if we need and require something better, we can try to make it that way with Xenomai. But Linux can also grow, and as you know, like Ubuntu and other distributions, Fedora, SUSE, etc., they have a graphic user interface attached to them, and they feel like a regular computer or like a regular operating system like Windows. But of course, the larger the Linux distribution, more memory and processing capability you require. So we try to optimize as much as possible the Linux kernel and just stick with what we need. Linux has become very popular on the ARM processors. Just want to mention here, this is Linus Torvalds. He is the inventor of Linux. I started this back in the 80s, I believe, or early 90s. And you can go and check his web page or GitHub page, and you can find the Linux kernel right there, and he continues to manage it. So it's quite incredible, the contribution of one individual, then a community of individuals, how much impactful it has become. One recent highlight of Linux is that it flew on Mars, on the Mars helicopter. So I'll have a picture of that coming up, but that's pretty amazing. So Vxworks is another operating system that is out there for the industry. Is a fully featured operating system, has been used in NASA for over 20 years since the Clementine mission. And just to mention about the Clementine, Dr. Trevor Sorensen worked on that mission. And so it's a highlight mission for many reasons. It has been used in many robotics applications, like the Robonaut and MER. It manages the system like with tasks and processes. So similarly to Linux, it has these features that are comparable. Now, the Vxworks is a commercial license, and there's a lot of tools that come with it. So diagnosis tools and things like that. But it's high cost. So there's these usually are for very very big missions that NASA and other agencies develop. It currently supports 32 and 64-bit processors, can run on Intel, ARM, PowerPC, and RISC-V, and can also run on multi-core processors. Next one I wanted to emphasize is the RTEMS, the real-time executive for multiprocessor systems. RTEMS is another real-time operating system developed since the 80s. It's a very lightweight operating system. There's no memory or process management necessarily on this one. So it functions differently from what we would do in Linux in terms of running the applications. But it also has some POSIX influence, and POSIX actually influence a lot of Linux development. So some of the elements are still similar, but not everything. RTEMS has been used in space flight, medical, and many other critical applications. So when you need to guarantee that real-time deterministic application, you want to use something like RTEMS or an RTOS. It currently supports many processors, ARM, PowerPC, Intel, Spark, RISC-V, MIPS, etc. And here's some of the specific features of this. So it manages file systems, multiprocessing. There's a shell in it, dynamic loading. It has the full internet stack from FreeBSD, which is also inspired by POSIX. And it has USB support and things like that. The license, it's under GNU. It's a general public license. And separately or differently from Vxworks, it's not a paid license. So it's much easier to get access to this. And again, it's been used in NASA and ESA missions throughout. Here's another example, the FreeRTOS. It's again a small and real-time operating system for embedded devices. It's licensed under the MIT license, which again is widely available, and people can actually change the FreeRTOS code. It's designed to be small and simple, but it does not have like fully functional features like you would expect in other operating systems. So this is where you really want to get your memory footprints as low as possible, and possibly power. All right, so that was just an overview of options that are out there. Now let's dive into a little bit more onto the PyCubed flight software and see how that works. So PyCubed is using this CircuitPython or MicroPython. It's a lightweight version of Python designed for microcontrollers. So here's some of the key aspects. So it has native USB support with serial port debugging. This is great because you don't have to create an interface specifically for programming and interfacing and debugging. This is something that most other microcontrollers require, and it's sometimes quite slow. So having this USB serial port debug availability is very useful. The CubeSat drive actually mounts as a USB flash drive, which is great again, because like you have your file system right there plugged into your other laptop or development computer. There's no compilation required. So many times compilation takes quite a bit of time with other microcontrollers, but in this case, there's no compilation, so it's handled internally. Uses a Python 3 programming syntax, which is becoming very popular, and that allows you to directly interface with I2C, SPI, UART, the CAN bus. So that all is great. It's an open source architecture. So again, anyone can go in and improve it or tweak it, fix bugs. It's also robust to fault tolerance and error handling, which is great because that is something critical to a mission. And it's also possible to do over-the-air software updates. So technically, if you want to change your software while you're in space, it's possible to do. So there's two levels of software on the PyCubes. There's the firmware level, and then there's the software level, as they call it. So the firmware level is written in the C code, and that's where the Python script gets interpreted. And then the software level is the high-level programming running Python scripts. And that's what you will be using. So most of you will probably not have to worry about the firmware level, although for minor things. And here's the repositories for each of these. So the PyCube software runs on the microchip AT-SAM D51. That's a microcontroller. And then this microcontroller and the board itself run at about 0.13 watts, as we measured it before. So very low power, nothing compared to the Beaglebone, as we will see. And then again, the software on the board is using MicroPython. These Python scripts are written for all the hardware components. So this includes the radio, the IMU, the GPS, the solar panels, etc. So all of these are run with Python scripts. And there's this main Py file that where everything starts. That's the main file where the executive threads on the PyCube starts, and then from then on, it calls the various other scripts. So on the right here, I've listed the software architecture for KAO, which is similar to your CubeSat. So here on the right, you have the PyCube board. And then on the left side, you have the OBC board, and you can see how they're connected and how the processes talk to each other. So you have the IMU, GPS, controller, power monitor. All of these are called and executed via these Python scripts. I want to take a little bit of pause here to talk about flight software design. Many times we like to jump in right into the software development without thinking too much. We're like, okay, I need to put some code here for the GPS, and then I need to put some code for the IMU. And we don't necessarily think about the bigger picture and the architecture. It is important to do that. So that's why this example here on the right that shows the overall architecture for the flight software of KAO. But there's these tools that allow us today to make a better job. So there's Unified Modeling Language. This is a framework that has been used for software engineering to develop these high-level abstracts of functions and flows in software. So it's a general purpose, block diagram framework, but it's quite used in the industry and it's good practice. So I would encourage you to take a look at that. More recently, an evolution of UML has led to the SysML, which is a systems modeling language. So this is quite used now for not just software, but also for physical systems and say in this case, the whole spacecraft. So there's this thing called model-based systems engineering, where you model your whole spacecraft or car or whatever engineering application you're working on. And you can have, say, on a spacecraft, the ADCS fully modeled in one block. And then you have, say, the orbit modeled in another block. and then say your power system model, and then you bring these blocks together, like literally blocks like you can see on the right. And those blocks have a standard way of being constructed based on the system modeling language. So again, we don't have too much time to look into these, but I would encourage you to do some reading about that. I will put some of that in the resources page at the end. The main idea I want you to take out of this is think about software, not just something that you jump into right away, but think about it in a architecture and framework way, so that all of you guys can communicate easily about what your software requirements are and all the different aspects of it. So now we're going to talk about the Beaglebone flight software. The Beaglebone runs Debian OS or some other Linux distribution, but typically Debian. And you can cross-compile your C, C++ code for the ARM architecture. What this means is that you have your regular machine, like your PC or laptop, and that runs, say, Windows or Linux, an Ubuntu distribution or something like that. You download a compiler that is targeted towards the ARM architecture, and you compile your code against that compiler, which then you copy those binaries to the Beaglebone and they will run. But they cannot run on your computer. That's why this is called cross-compiling, because you compile in one computer and deploy in another computer. That way you get the best of the two worlds, where you get a fast machine to compile your code and then your embedded development machine to run your code. So we have Qt Creator and Visual Studio Code as examples of what we call IDEs, or integrated development environments. And there's others, but these are typically the ones we use. And then we're going to be using Cosmos Core flight software for these. And some of the functions that we will be using from Cosmos Core is the agents to manage the executive processes, to the payload management, the radio management, state of health management, and telemetry and control. Some of these functions will be shared with PyCubed and partially implemented there as well. So there's going to be a bit of a breakout on the code, but these are the main functions that we'll be working on. I have shared this slide before with you guys, but just as a review, Cosmos stands for Comprehensive Open Architecture Solution for Mission Operation Systems. And then this was a NASA-funded project back in 2010 and through 13. So I actually have a timeline for this. And Cosmos is bigger than just one particular flight software. There's tools for the ground, for the mission operations on the ground, for simulating the spacecraft and the orbit dynamics and attitude dynamics. So it's a comprehensive set of tools. But many of these tools are being converted to Cosmos Web now. So we're going to be mostly using Cosmos Web, which is the newest version of these tools. The conversion has not been completed yet, so that's still work in progress. But so you guys know. And yeah, I have here just a bit of a history on Cosmos. So this software was developed to support the design, testing, and flight operations of one or more satellites. In fact, its design is for satellite swarms and constellations and managing many, many satellites. But it can also be used for one satellite, and that's been so far the main use for Cosmos. So in 2010, we initialized the development of Cosmos under a NASA contract. Through 2015, we developed Cosmos Core for Hyakasat flight operations. Through 2016, I worked a lot on Cosmos and developed guidance navigation control algorithms and ran some results for my PhD. In 2017 and through 19, we developed Cosmos Core for Neutron 1 CubeSat. And then now we're working on Cosmos Core and Web and other tools for the high-tech CubeSat. Yeah, so this gives you just an overview of where Cosmos, how Cosmos has been developed over the years. So Cosmos can assist in all aspects of a mission, from actually testing through integration, through launch operations, etc. And we use standards, industry standards. So we're trying not to necessarily reinvent the wheel, but adopt the best standards out there, somewhat modern standards for embedded devices, communications, and message passing, sensor data collection, etc. So we use a web framework philosophy, and the telemetry is transferred with what we call JSON or JavaScript object notation. And this data is stored on disk or shared over the network in this format. It can also be in binary format, but typically in JSON. The command and control is implemented as native OS programs. So when you actually run a command via Cosmos, you're running a command like you would be on a Linux machine. It's very similar. Telemetry and commands are transferred as either files or network packets. We are heavily encouraging the use of files for various reasons. So that's our preferred method. And then the network communication is performed via UDP packets. That's a very common way of transferring data nowadays, like even Zoom is mostly a UDP packet system. So is Cosmos. We generalize complex devices. So for instance, every subsystem on a spacecraft has voltage and current. So that device concept is propagated throughout every subsystem. But there's other elements like that, like mass and number of sensors and things like that. So it's easier to see when you actually implement that. Modularization. So we modularize the subsystems and devices as we embed them into an agent concept, a software agent concept. So a particular agent could be an agent reaction wheel or agent control. In that a particular aspect of the agent uses a driver to talk to the device. So this way it's easier to modularize the codes and merge it with other agents and even other functions in other spacecraft. And we reuse components. So we try to create generalized namespaces and components so that say that this reaction wheel for this particular satellite has this number of telemetry points and commands. We can use another reaction wheel that has a similar set of commands and telemetry points And then these two reaction wheel manufacturers now are supported within Cosmos. Let's talk a little bit about the Cosmos Core agents. So these are the persistent programs that are installed, in this case, the Beaglebone. So we have agent exec. So this gathers all the state of health information from other agents, manages the time for the spacecraft, manages the command queue. So when a new command is received, or if there's a list of commands, it knows when to trigger those commands. It also keeps a log of what's going on. So of the telemetry that's been received, and also the commands and other things like that. There's also a file transfer agent. So this file transfer manages the upload and download of files. And because spacecraft come over a ground station at a particular time, but then that contact is lost, and then you have to wait another few minutes or hours or days to regain that contact, you have to have a very forgiving transfer protocol. So just FTP would not work. So we have developed this file transfer agent that allows us to reinitiate that transfer when a communication is gained again. Then there's the network tunnel agent. So this allows us to transfer messages from a subnet to another subnet. And it could be very handy, especially on the ground when we're doing testing. But also in the spacecraft when there's a direct contact with the spacecraft. Then we have radio agents. So the radio agent manages everything about the radio, so the transmission and reception of data through the radio. If we tie it to agent tunnel, we can actually talk to the satellite as we would be talking to a device on the internet. So pretty useful. Here's just a quick diagram of Neutron 1's agent implementation on the flight OBC and some of the subsystems that it was connected to. I would encourage you guys to develop some simple diagrams like this one for your particular mission. And now here's a couple examples of specific agents that you can implement. So the ones I've presented before, they're generic agents. Pretty much every mission uses them. These ones are more specific to your particular mission or each mission. So there's the electrical power system agent or agent EPS. So this will control everything that has to do with turning on the switches, turning off battery management, deploying solar panels if there's deployables and things like that. And then we have the attitude determination control subsystem agent or agent ADCS. So that, similarly to agent EPS, controls every aspect of the ADCS. So the torque rods, the reaction wheels, the telemetry, the control authority and everything. So the estimation as well. So that agent ADCS can be a fully fledged ADCS control algorithm with all the telemetries and everything, or it can also be targeted towards collecting data and talking to a specific ADCS device. Like for Hyakasat, for HiTi, we're actually talking to the CubeSpace hardware, which handles all the control and estimation algorithms. But we still wrap that into the agent ADCS for the main command and control. So here's an example of the HiTi Cosmos Core flight software. We run all these agents in the Unibap IX5 computer. So we have agent exec, agent file, agent tunnel, different agent radios, because we have various radios. We have agent EPS, agent ADCS, agent ISC. So these agents, they're all customizable somehow, some more than others. So it really depends on the mission, but as you can see, we have this agent exec file and tunnel. These are the generic agents and radio that you can just borrow easily from another mission. But then you have to implement specifically agent APS, ADCS, and others that are required for your mission. So lab work here that I suggest is that you guys come up with a diagram like this one, where you're going to start to think about what are the agents that we need for our particular mission. And yeah, just create that list so that we can then discuss more about that. Here's an example of the flight software and communications architecture for high-tie. So we have the payload OBC and the ISIS OBC talking to each other. There's a command and control capability between the two. And then each of these radios has each of these computers have its own radio network that goes to the internet. And then Cosmos runs here the mission ops server to talk to these. Again, lab work is to update this diagram or create a diagram like this one for your particular mission. You will probably not be talking directly to the internet in this case because we will be using our KCC ground station. So here, instead of internet, you would be using KCC. And there will be other changes. So just take this as an example and develop your own application. And here's another example of the flight ops and communication information flow. So you have the camera transferring data. It would be good to indicate in your case what kind of data it is and what the protocol is to the payload OBC and the payload OBC to the IOBC, and how these two computers are specifically connected to the radios and how the telemetry and control flows between these. So again, another suggestion for lab work is to update this diagram or make one for your EPET mission. And I think this is the final example. So here is a more detailed view of the payload data flow. So in this case is for the high-tie camera. We have the camera connected to this FPGA on the Unibap computer, passes over to the CPU, to the disk, goes back to the CPU, to the GPU for processing, etc. So in your case, it's not as complicated, but still you have a couple of computers, you have a payload. So just show how the payload data flow goes so we can understand from point A to point Z, how is it that you're going to transfer that data, and then how does that data get to the ground? Okay, so let's talk about other flight software frameworks. We have talked about Cosmos and how that can be used for the Beaglebone. It's not the only solution that could be used. There's others out there that you guys should be aware of. So NASA has actually encouraged open source software for a while. We are with Cosmos, one of the projects that came out of this effort from NASA. But you can look at GitHub and find a lot of open source projects that are available out there. In particular, if you go to NASA's GitHub page, you'll find a lot of great stuff. You can also find code that is not just on GitHub, but also at this website, code.nasa.gov. This code, or usually this software may actually be for just US only people and things like that. That's why they don't list it just on the GitHub. But either way, it's good to browse those resources. And here's a quick table on the most comparable solutions out there to Cosmos. So we have for flight software, Cosmos Core, as you've been made aware of. But NASA's developed these core flight systems, so CFS. And in many ways, it's like Cosmos, and it's been used in several missions. There are differences to Cosmos, one of them being that Cosmos has been designed for multiple satellites from the ground up. Core flight system, as far as I understand, it's been designed for particularly targeted single satellites or other devices like that. It's been used in UAVs and other like robots. So it's also flexible in that sense. We have also Kubos. Kubos has been dropped. Its support has been dropped by the company, the mother company. So the community now keeps the software going. But Kubos, in many ways, acts as the middleware to the satellite, so that it connects to the different subsystems and can also do message passing and all of that to the radios. Now, for ground software, we have Cosmos Web, which we're developing and will be the main interface for the visualization of Cosmos. We also have Ball Aerospace Cosmos, and its name could be sometimes confusing. So this other Cosmos is also capable of receiving telemetry, processing commands, sending commands, plotting, and telemetry logging. So many of the functionalities that we do have also with Cosmos Web. And then there's Open Mission Control software. It's a NASA software that has been developed for mostly the ISS operations. So it's for bigger operations than Cosmos has been developed for. Cosmos, as our original Cosmos, has been developed for small satellite missions mostly. But all of these tools are worth checking out and exploring. If you guys have the time, I would encourage you to do that. So here's a bit of a dive onto the NASA CFS. So the core flight system is a generic flight software architecture framework. It's been used in all these missions, so it has quite a pedigree. And in fact, a notable one is this James Webb Space Telescope. So the core executive goes along with the core flight services. So it's a set of applications, runtime environments developed by NASA's Goddard Space Flight Center. So Cosmos Core bundles all these different aspects of the software into the main agent functionality. Here they have broken it apart. So it does messaging, timekeeping, events and table-driven commanding and configurations. It's open source and currently released under the Apache 2.0 license. So here's some of the links for you guys to check it out. F-Prime has been developed by JPL, and it's actually currently now running on this Mars drone. So it's probably the open source software framework that has gone the farthest in the universe. So that's pretty cool. It's running Linux and F-Prime on this little drone on Mars. It's also being used on the Stereo, CubeSat, and some others. So let's talk a little bit about development environment and tools. Software development before used to be, one person on its computer developing the software, delivering to the client, and that's it. Of course, nowadays it's much more than that. So you have a big team of developers, you have to collaborate. So you need tools to be able to do that. It's just not like you cannot zip your code, email your code to your colleague, and it continues to develop it. I've actually done that many years ago. It's not a good way of developing code. So GitHub has come along and uses underneath the Git client and server capability. A curious fact, Git actually was developed by Linus, who's the same developer as Linux, to support the Linux environment and development. So pretty cool stuff. Atlassian Tools. Atlassian is a big Australian company that develops tools for software developers. So they have a Git server and Subversion. Git and Subversion are pretty much the same capability, or like content management or version control. But Git has become more prominent in the developer worlds. SVN is a bit older. So, but anyway, both tools are very capable. Atlassian also has a bug tracking and issue tracking system called Jira, as a documentation system called Confluence, and continuous integration called Bamboo. So Atlassian has a full suite of tools to integrate full software development team. GitHub also has some of these other functions, but not as developed as Atlassian. So yeah, it's important to keep up to date with these tools and know how to use them, especially for good software development and good practices. Speaking of best practices, it is important to learn how to better do software rather than just hack some software into it. So flight software projects can be very complex and overwhelming, and this is true. I can attest to that. So, and why is this? Because you have hundreds, maybe hundreds of thousands of lines of code. You have, it's costly. You have to have a team that runs this software. You have reliability issues, can be difficult to test and things like that. So and that's why it's good to go off of it rather than developing your own software from scratch that can be prone to a lot of errors, no reviews from peers and things like that. You want to borrow from software that has been developed over the years, has been tested, validated, and yet it can be flawed. But that way you can build upon something that is already done. So you simplify your development process by using an existing software framework. So here's some of the best practices. Create a plan. Always think about how are you going to do this software, how to break it apart in manageable chunks. That's why I was giving you suggestions for the lab work to create those diagrams, because that will start to help you understand how to break that software and maybe assign people and tasks to each individual component. So try to put a schedule together and budget if that's applicable. Use version control tools like Git or Subversion. This allows you to track changes, to collaborate between members. You can check if there's bugs in the code or see where bugs were introduced. That's a much better way to handle software development. Use code reviews. So ask your colleagues to go and check your codes, ask questions about it. Maybe they're not a software developer, but they might actually know about your mission and know about what you're trying to do and ask pertinent questions. But even better to do it with someone who knows the code and can help you validate the code and test the code. Document as you go. This is one of the hard ones for software developers and for engineers in general, is to document the work that you do. So one way to do this is to document it as you go. So when you create a new function, a new software library, just put a header and show, who built this or who programmed this part of the code, what's its purpose, what's the input, what's the output, and things like that. So that when somebody comes in, they don't have to read through your code and try to figure out why or how did you do that. Doxygen is a tool that actually allows you to extract comments from the code. It's very useful. Excuse me. Software testing is another good practice. So you don't want to just build your code and leave it as it is. Test, test, test. It's usually the main thing that we say about spacecraft development is that you have to test not only your code, but all the subsystems to quite an extensive range. So you have unit testing or component level testing. You have manual and interface testing, integrated testing. So there's all these kinds of tests that should be used. And then finally, we have continuous integration. So continuous integration is what we mean by having the machine, say like your computer or GitHub or one of these tools out there, to build the code for you. When you submit a new, commit to the code, it automatically detects that, builds the code, and then will give you a report if there's a bug or an error when compiling that code. And then it can also run your tests, your unit tests. And then it can tell you, okay, it's all passed, or you have a problem here. So this continuous integration allows for a much quicker detection of problems in your code. And it will even allow other peers, other colleagues of yours, see if you committed something and it has a problem, they can go and automatically fix that problem in case that you didn't see that. So there's a lot of advantage. Today, modern software is built with continuous integration all over. And NASA has built a procedural requirement document called NPR 7150.2, now version C, so that people can actually follow these best guidelines and procedures and match it against something that NASA vouches. So if you want to check out this document, it's available online. Just click this link and you'll get there. So back to our mission. We have a lot of code to develop. We have code for the onboard computer, or the Beaglebone, and we have also code for the PyCube board. And we have developed a lot of agents. We have developed a lot of codes for the PyCube. You got to make sure that you, first of all, get that code and put it on your separate repository so that it's now managed by your team and can be evolved from there on. You don't want to go and mess up someone else's or other project's code. So I would suggest you guys create a GitHub page for your mission and copy the relevant code into that and start testing it and checking what can you reuse, what can you develop. And again, here's just an example of Ao's flight software block diagram. I'd like you guys to update these to your own mission concept. And if you have questions, we can talk about it. But by now, I hope you have a better understanding of what your software will look like. And if there's things that are missing here, please add them. If there are things that are not applicable, please delete them. as necessary. All right, so flight software is definitely key to mission success. Without flight software, you just have a dead brick in space. The challenge with flight software is related to its complexity, not necessarily, and the complexity of the mission. So not necessarily the size of the mission. So you can have a huge spacecraft, but very simple software, and a small CubeSat with a very complex software. So it's not because it's small that it becomes easier. There's some typical concerns in terms of scheduling issues and implementation issues during the integration and testing phase. So that's why it's important to test your software. Look for limit conditions so you can find these potential problems that don't occur when you're running things nominally. Developers have a tendency to add additional features at the very last minute. So what's important is develop everything that is important early on, and then test, and avoid adding new features at the last minute. This creates problems. The simpler the software is, the more likely your mission will be successful. So do not try to complicate your software. Software is complicated by itself, but trying to make it fancier or better looking or whatever doesn't necessarily mean that you'll get a better mission. Use the NASA guidelines for flight software development. Exercise and test your software. Again, stressing this all over the place. You want to, again, check critically if new features are being added and if they're really necessary or not, and try to plan as carefully and as you can so that you can have a favorable outcome. Software is something very tricky, and you don't want to be doing software at the very last minute. This happens all the time, unfortunately, but you want to try to plan ahead as much as possible. So again, just to close out, we have the PyCube that uses MicroPython. It's an open source framework being developed by Adafruit, holds a lot of promise, especially to reduce the development time and the debugging time. Beaglebone has become a very popular open source hardware platform, which can also be programmed with the open source software platform or framework, which is Cosmos Core. And both PyCube and Beaglebone Black with these tools have flight software heritage. So, which is great. You're not starting from scratch. You're actually developing what we have done for previous missions and others. So with that, let's see. Oh, we have homework. So I would suggest that you, at your own time at home, check this video. It's a short video about this lady Margaret Hamilton, who developed the first software that was sent to the moon for the Apollo guidance and navigation module. So that's pretty cool stuff. And then I would also recommend that you prepare the diagrams listed on the slides before. And here's some of the resources for the lecture. So thank you very much, and I will see you next time.